Great. Welcome to class 2. As a reminder, you have these items that you need to memorize. You need to be very comfortable with them. Some of them I imagine you already are, such as the equation for kinetic energy is 1/2 mv squared. Sure, you saw that even in high school. So just making sure you're familiar with some of these concepts that I'm sure you know, and then making sure you're taking time to learn some of the ones that maybe are a little newer, such as force is mass times acceleration. Work is force times distance, and then how we represent a joule and a watt and what these are associated with. When we're looking at thermodynamic problems, for the first 5 chapters of the book, we're going to be looking at problems that are operating in steady state. So when we're looking at steady state or steady flow processes, we're looking at systems that have no change with time. They're not a dynamic system. They're not transient. If we look at a system at 1 p.m. or we look at a system at 3 p.m., it's going to be the same system. So a process during which fluid flows through a control volume steadily. Your mass coming in is equal to your mass coming out. It is steady flow. We can look here, we have in a set control volume or box or piston, if it's at steady state, the mass coming in is equal to the mass coming out. So another way of working with this is we're going to be saying steady. Sorry, gotta grab my notes. Steady flow process is where there's no change over time. And a fluid flows through a control volume at a steady rate, steady or unchanging rate. And the main way we represent this is the equation mass coming in is equal to mass coming out. So at a steady state system, the mass coming in is equal to the mass coming out. That's a major concept. So when we come back to our PowerPoint here, we can see once again, mass coming in is equal to mass coming out for steady state systems. When we're looking at thermodynamic systems, there's also about 4 laws that all thermodynamic systems undergo and use. So the first of these laws is the zeroth law of thermodynamics. This is saying if you have 2 bodies that are in thermal equilibrium with a third body, so if you have a, if you have a cup of water and you have a table and they're in thermal equilibrium with one another, then they're also in thermal equilibrium with a third body, which would be like the air. So if 2 bodies are in thermal equilibrium with a third body, they're also in thermal equilibrium with each other. Essentially, this is the reason why thermometers work. So if everything's in thermal equilibrium, then anything that you measure should be the same as a thermal equilibrium with something else. It is kind of like a very basic, simple assumption that we make about things, that if you have 2 items in thermal equilibrium with each other, then any third item in thermal equilibrium with one of them will also be in thermal equilibrium with the other. It's not a super important law that we use a lot, but it is one that we have to assume exists. One important law that we do use a lot is the first law of thermodynamics. So the first law of thermodynamics is the conservation of energy principle. Energy, like matter, cannot be created or destroyed. It can only be transferred. So if we are to go back to our notes, here we have the first law of thermodynamics. First law of thermodynamics. First law of thermodynamics states the conservation of energy. conservation or the conserving of energy, which is also saying energy cannot be created or destroyed. Energy cannot be created or destroyed. And the main way we represent this, energy coming into a system has to be equal to the energy coming out of a system. It may change forms, it may transfer, but in a given system, energy has to remain constant. It's conserved. It's a law of thermodynamics. Coming back to our PowerPoint, we can see that this is even related to our own body. In order for you to do something like wrestle, you need to be consuming energy. So you need to eat a power bar or eat breakfast, and then you can store energy inside your body in terms of fat or in terms of sugars, and then you can expel energy. So if you eat a big piece of cake and then you work out a little bit, whatever energy is not being expelled in your working out is also stored. But overall, we're still having a conservation of energy. Cannot be created or destroyed, only transferred. The second law of thermodynamics is a little more esoteric and difficult to deal with. Luckily, we don't start looking at it until the second half of the class. But the second law of thermodynamics says that energy has both quality and quantity, and that real processes occur in the direction of decreasing quality of energy. So the way energy is transferred is often in the direction of the decreasing quality of energy. A lot of times this means that heat is dissipating. That's kind of a law saying that heat dissipates. If you guys have hot coffee, it's going to eventually slowly dissipate into the cooler environment where the quality of the energy is less, confined, less organized. It's kind of just dissipating. So coming back to our notes, we can see the second law of thermodynamics, second law of thermodynamics. And this states that energy has quality and quantity. Energy has quality and quantity. And that actual processes flow towards decreasing energy. Actual processes flow towards decreasing energy quality. So as an example, heat dissipates. All right, coming back to our PowerPoint, we can look at some examples of this. So for the 0th law of thermodynamics, if you have a beautiful iced coffee and you're in your house and your air conditioning's on and you leave your iced coffee on the table, eventually your iced coffee, the table, and the air in your house are all going to come to the same temperature. So when the iced coffee and the air are at the same temperature, is thermal equilibrium with each other, there's no more heat exchange happening, then we can assume that that iced coffee and the air are also in thermal equilibrium with the table. Once again, 0th law of thermodynamics essentially states that thermometers work. If you take a thermometer and you put it in somewhere and you're assuming that it's in thermal equilibrium with something, then you can say that it's in thermal equilibrium with whatever else is interacting in thermal equilibrium with that item. The first law of thermodynamics is the conservation of energy. Energy cannot be created or destroyed. If you want to go ride a bike or work out, expel some kinetic energy, first you need chemical energy in the form of food, sugar. So we eat food, chemical energy. We convert it in our body through exercise to chemical energy. Kinetic energy. We have light energy in the form of UV light coming from the sun that are converted through photosynthesis into chemical energy. So while we have kind of a different form of energy, it looks different, we're using it in a different way, we are not creating any new energy, we're not destroying energy, we're just transferring it from somewhere else. Rocket launchers are another example, right? In order to get the rocket to have kinetic energy, we need the chemical energy of the rocket booster. The second law of thermodynamics is the one that states that processes are always going towards lower quality energy. We're always going towards more entropy, more chaos, more entropy is always increasing. So if you have a washing machine that's getting electrical energy that's from the wall, really nicely delivered, and then converting it into mechanical energy in the, machine that turns your clothes around, that energy is going to be converted into low-grade thermal energy. Your clothes will get warm, you open the door, the heat slowly dissipates into your house. So the energy is flowing from this nice mechanical energy into kind of slowly dissipated heat. Energy is always and inevitably flowing from higher concentrations, more condensed, more organized forms of energy into lower concentrations. This is in the natural world, this is in our home, this is kind of just a rule. If you want more information about these laws of thermodynamics, you feel a little behind, here is a Khan Academy that's discussing them. And I really like Khan Academy in general if you haven't already watched their videos. Reviewing a little bit more, there are 4 laws of thermodynamics. I haven't talked about the third one yet, but the first one is that thermometers work. The second one is you can't win. You can't break even is the second one, and you can't get out of the game is the third one. So explaining these a little bit more. The first law of thermodynamics, energy is conserved. So you can't get something from nothing. You're only ever going to have what you have. And then second law of thermodynamics, you cannot break even. You can only return to the same energy state. You can't return to the same energy state. You're always going to be losing heat. You're always going to be increasing in disorder. Entropy is always going to be coming to get you. And the third law is you can't get out of the game. And the third law is stating that absolute 0 Kelvin is unobtainable. We're not able to get to 0 Kelvin. So the third law is stating you can't get to 0 Kelvin. This is the reason we use the temperature scale of Kelvin, because it is like the absolute 0. And there's no formula associated with the third law, so we don't really use it in the class, but it is interesting to know. And we have gotten very close to 0 Kelvin. We've gotten to 450 picokelvin. So very, very, very close by researchers at MIT. And really cool things happen to matter at these really, really low temperatures. They become super fluid and super conductive, and they don't behave like a normal state of matter. So it's interesting to look at some videos or just Google Bose-Einstein condensates. They're really cool. All right, so moving away from the laws of thermodynamics, we're going to go into heat work and internal energy now. And I'm going to start making some tables. So please make some room in your notes. All right. First, I want to state briefly the state postulate states that in order to define a system, we need to have it be specified by 2 independent intensive properties. Typically, these are temperature, pressure, or volume. All right, coming back to our notes. I'm going to clear these, clear all drawings. Here we have, I'm going to make a table where we're looking at quantity, definition, a positive term, and a negative term. So if we have a letter Q, this is representing heat flow. Heat flow is represented by the letter Q. And if we have a positive Q, that means heat is flowing into the system. Heat flow into the system. Similarly, if we have a negative, that means that heat is flowing out of the system. Heat flows out of system. Next, we have work, represented by a W. And if we have positive work, this means the surroundings do work on the system. If we have negative work, that means that the system does work on the surroundings. If we have internal energy, that's going to be represented by capital U. This is internal energy, represented by a U. And if we have a positive delta U, delta meaning change in internal energy, change in internal energy. So if we have a positive change in internal energy, that means the internal energy of our system is increasing. Internal energy of system is increasing. Internal energy of the system increases. Similarly, if we have a negative change in internal energy, that means the internal energy of our system decreases. All right. Moving on, we can look at how we interact with some of these quantities, heat, work, and heat flow, work, and internal energy. So the way that we look at these often is in the form of process diagrams. Process diagrams are where we have some sort of property, property B, graphed against another property, property A. These properties are typically common properties in process diagrams. Common properties used in process diagrams are temperature, pressure, and volume. We have these property diagrams, and then we're going to plot our system where we have some sort of initial state 1, and then we have initial state 2, or I'm sorry, final state 2, so initial state and final state, and then we have a process path. So this is our process path. So we have a process, any change that a system undergoes from one equilibrium state to another. Any change that a system undergoes from one equilibrium state to another. And then we have a path, which is a series of states, during which a system passes during a process. A series of states which a system passes during a process. A series of states which a system passes during a process. So as you can see, if we come back to our PowerPoint, we have property A, property B, state 1, state 2, and our process path. So if we're looking at something like a piston that's compressing, we can plot this on a process path. So typically we have volume and pressure process diagrams. And if we're looking at a system that's compressing, so it has like a fluid in here, it's compressing the fluid down. So it's reducing the amount of volume and likely increasing the pressure. It's kind of like if you have, trying to think of, like if this would be like in a car or in a factory or something, you're kind of compressing down the fluid that's in this piston system. So we have our starting volume and our ending volume. Our volume here might be something like, 10 liters, and our volume here might be 2 liters. So we're decreasing in volume, and then we're increasing in pressure. So our pressure, something like here, increasing to here. And this is our initial state and our final state. So we decreased volume, we increased pressure, and along this compression of the piston, this is the path that the system took. So it's not directly linear, it's passing through these different pressure states over time. All right, and then the isothermal process, we're going to make another table before we start talking about those. So here we're going to have a table where we have process, name, equations as our table headings. And one thing to note, when we're looking at a simple compressible system, we use a basic equation that the change in internal energy is equal to heat flow plus work. So in something like a basic piston system, this is the equation that we use. I'll explain more of this throughout classes, but for now, just know that this is the equation that we use. You don't have to memorize it, just know that it's there. So if we have a process that has no heat flow, this process is called adiabatic, where your heat flow of Q is equal to 0. And if we use this equation, delta U equals Q plus W, well, Q is equal to 0, so delta U just equals W. Our change in internal energy is just equal to the work that's done in an adiabatic process. If we're looking at a process that has a constant volume, this process is called isometric or isochoric. And our change in volume is equal to 0, or our starting volume is equal to our initial volume. If we're looking at this equation again, our change in internal energy is equal to heat plus work. Work is equal to our pressure times change in volume. So here's where our volume term is. It goes to 0. So our equation is just our change in internal energy is equal to heat flow. If we have a system that has constant temperature, this system is called isothermal. It's where our change in temperature is nil and our starting temperature is equal to our ending temperature. Looking at this equation again, our equation for internal energy, which we haven't gone over yet, is MC delta T. Here's where our temperature term is hidden. So our equation is just rearranging. Negative heat flow is equal to work. Finally, if we have a constant pressure, this system is called the isobaric. Our change in pressure is nil, or our starting pressure is equal to our finishing pressure. If we look at this equation, our pressure term is hidden in this work term, where work is equal to the negative pressure times the change in volume. So this is our equation that we're working with here. We're not dealing with internal energy or heat flow. All right. So if we're looking at a system, here's the property diagram. We have volume as one property, pressure as the other property. And we have a system that starts here. This is state 1 and goes here to state 2. What sort of system is this? We can see pressure is changing, but volume is not changing. So this is considered to be, your change in volume is 0. This is considered to be an isochoric or isometric system. Similarly, if we start here and we end here, where our change in pressure is equal to 0, then this system is what? Isobaric, constant pressure. If we have a system that starts here and ends here, and I tell you that the heat flow is 0, this system is an adiabatic. And if it starts here, ends here, and I tell you that our change in temperature is equal to 0, this system is isothermal. So isobaric and isometric are the ones that you can see based on this graph. Isothermal and adiabatic, you need some additional information provided. All right, coming back to our PowerPoint, here's an example of an isothermal system, isothermal where the temperature is being held constant. So we have volume and pressure. As our volume is decreasing, our pressure is increasing. This is all at the same temperature. And our equation for isothermal systems was negative Q equals W. Isobaric processes, this is where our pressure is being held constant. So our pressure here, as you can see, is a straight line. We have two different isotherms, so two different systems being held at a different constant temperature. This one might be held at 30 degrees C, and this one might be held at 60 degrees C. And this isobaric, constant pressure. So as we're holding the pressure constant, we can have this expanding volume where we have maybe heat flowing in. And our equation for isobaric systems is work is negative pressure times change in volume. If we're looking at an isometric process, this is where the volume is being held constant. So volume is being held constant. We can run the system at two different temperatures, have different heat flowing in. The piston is set in one spot, and our equation becomes our heat flow is equal to our change in internal energy. Adiabatic process is where we have no heat flow. I think of this as being in a hydro flask or being in a big insulated tub. We have no exchange of heat. So it's an adiabatic process. If we look at our changing volume, our changing pressure, and our changing temperature, it'll all be isolated to within the piston. And so our work done is equal to our change in internal energy. Here's the table that we wrote. Constant temperature is isothermal, constant pressure is isobaric, constant volume is isochoric, no heat flow is adiabatic. And these equations are all manipulations of the original equation that the change in internal energy is equal to heat flow plus work. On Friday, we're going to go over some example problems and in-class activities. So please come prepared to class in person or on Zoom. Review these nomenclatures and these basic equations. Please finish reading chapter 1, and homework 1 should be completed within the next couple of days as well. All right, have a great day.